first thing we'll do is we'll finish up talking about binary variables, and then we'll talk about adjusted R-squared, and then using log forms. Okay, and there's a question, if you look back on one of the old exams, there's a question that makes heavy use of binary variables, mostly on the independent variable side. And so you can use independent variables as intercept shifters, or you can use them as slope changers as well. And so to illustrate, we have the following model. So let's say yi equals so di is some dummy variable. Xi. So we have di, remember, is a dummy variable. So let's say di is equal to 1 if female, 0 if male, right? Or really 0 otherwise. Which I know it's the same either way, but it's nice to just have the 0 otherwise, because then it kind of reinforces the fact that the two are mutually exclusive. And so here you have a case where if we ignore beta 3, we basically have two parallel lines where this is beta 0, and then this gap here is beta 1. So beta 1 shifts up the slope. In this scenario, both of the slopes would be the same though. But we have this binary variable. So if we look at what's the expected value of y given d equals 1, it's going to be equal to beta 0 plus beta 1 will be the intercept. And let's see, beta 2 plus beta 3 will be the slope, right? Because this equals 1, so we have beta 2 xi plus beta 3 xi. Conversely, if it equals 0, we just have beta 0 plus beta 2 xi. So in this case, what we're going to have, and so this slope here is going to be beta 2. So if we have this other model, what we're going to have is, let's assume beta 3 is negative. You could have something like this, right, where they actually do intercept. So here the slope is going to be beta 2 plus beta 3. Okay. So you could have different intercepts and different slopes. And so one of the questions in there is, what about, the question is, can you test whether the slopes and the intercepts are both different? So you have a joint hypothesis. Your hypothesis, if you're looking at here, is basically that these two equations should be the same, right? So whether d equals 1 or d equals 0 shouldn't matter, is what that's asking. And so your hypothesis is essentially that beta 1 and beta 3 are both jointly equal to 0. Okay, and your null is that one of them is not. Okay, so anytime we have a joint hypothesis, so anytime there's more than one restriction, we have a joint hypothesis. Anytime that happens, we have to do an F-test. So we have a restricted model and an unrestricted model. Here's our unrestricted model, and then for our restricted model, we impose this, which is actually going to just be that model right there, right? Beta 0 plus beta 2. And so, more formally, we have, this is our restricted model. So we could test the statistical difference between these two. You know, we run each one of these regressions, we get R squared, we calculate our F statistic. If that F statistic is greater than the critical value that we look up in the book, then we reject the null hypothesis. Otherwise, we don't. Okay, so take a look at that question. That's some good practice, I think, with binary variables. Another thing we talked about was when we had more than one binary variable. So we talked about, you know, what if you have something like season? So you have, you know, fall, winter, spring, and summer. If you include all four of them, you have perfect multicollinearity. So you have to exclude one of them and then put that in your regression. And so then, at that point, let's say we have something like that where we had yi beta 2, and let's say this was fall, summer, spring. Okay. And so each one of these are binary variables. Let's say these are, I don't know, let's say this is housing price. This is square feet. And so the assumption is, you know, I don't know, somebody comes out and looks at a house in the spring, and, you know, flowers are in bloom, and the temperature's nice, they pay more for it, let's say. And so again, we can look to see if we compare the expected value of y given fall equals 1. The expected value is beta 1 plus beta 2 as the intercept plus beta 1 xi. Okay. And so we compare that to the expected value of y given winter equals 1, right? Which is our excluded variable, which is just beta 0 plus beta 1 xi. Okay. So, point is, this hypothesis that beta 2 equals 0, what we're looking at, how do we interpret that beta 2, is going to be, it's going to be an intercept shifter relative to winter. So when we have multiple variables and we exclude one, our interpretation of that is going to be, is there a relative difference between the omitted value? So is there some premium in fall relative to winter? So you come and look for a house in winter, and it's covered in snow, and it's windy outside. Is there some kind of premium if you come out there and it's comfortable weather? You know, everyone has their Texas Tech flags out. Maybe there's not. You know, the leaves are starting to change color, and maybe like, oh man, you know, I want this house to be what? It's just a really good neighborhood, but it doesn't look so good when it's covered in snow. So maybe there's some premium. But the point is, whenever you exclude a variable, all of your other coefficients are going to be relative to that omitted variable. Okay. So here, beta 2 is interpreted as some premium in fall relative to winter. Okay. Okay. The other thing we can have is a binary dependent variable. So we started talking about this a little bit. I'm not sure, do I have an example? So the example is yi equals 1 if new TV recently purchased. Zero otherwise. So basically, if you've purchased a new TV in the last 6 months, that observation has a 1 and 0 otherwise, right? So people might be interested, you know, if the likelihood, you know, so there are a lot of, you know, tax credits that were given this past year, and you know what a lot of studies would want to know then is, okay, you give these tax credits, but what did the money go to? And so this would be one situation where you might want to see, well, does